Hello, and welcome. Today, we are continuing our study of set operations. Our focus for this lesson is intersection. This is Module 1, Lesson 6. Before we look at the formal mathematics, let's start with a simple intuitive idea, finding common ground. Imagine you have a music playlist. It contains Song A, Song B, Song C, and Song D. Now, your friend also has a playlist. Theirs has Song C, Song E, Song F, and Song G. If we look at both lists, what do they have in common? Right, Song C is in your list, and it is also in your friend's list. This shared item, this common ground, is the core concept of intersection. Now, let's build our foundation by comparing union and intersection. In our last lesson, we learned about union. Remember, union is based on OR logic. It combines everything, anything in set A, or in set B, or in both. Intersection, our topic for today, is based on AND logic. We aren't looking for everything. We are only looking for the elements that are in both sets at the same time. It's just this overlapping, shared region. So let's formally ask, what is intersection? The intersection of two sets is the new set containing all elements that are in both sets simultaneously. The symbol we use for intersection is this, an upside-down U. Let's use a concrete example. Set A contains the numbers 1, 2, and 3. Set B contains 3, 4, and 5. Let's visualize this with a Venn diagram. Here is set A, and here is set B. Let's place our numbers. 1 is only in set A. 2 is also only in set A. Now, what about 3? 3 is in set A, and it's in set B. So it belongs right here, in the shared space. 4 is only in set B, and 5 is also only in set B. So when we ask for the intersection, we are only looking for that shared region. The only element in that space is 3. Therefore, we write A intersects B is the set containing just the number 3. Here is a key insight about all set operations. Even if an element is in multiple sets, it appears only once in the final set. This is because sets, by definition, contain distinct objects. There are no duplicates. Now, let's look at the formal mathematical definition. We can express this using set builder notation. It looks like this. We read this as A intersects B is the set of all elements X such that X is an element of A, and this is the crucial part, X is also an element of B. It must satisfy both conditions. This leads to an important question. What about disjoint sets? What happens if the sets have nothing in common? For example, let's say set C is 1, 2, and set D is 6, 7. Visually, they don't overlap at all. They are two separate, distinct sets. So what is their intersection? Since nothing is shared, the result is the empty set, which we write with this symbol. When the intersection of two sets is the empty set, we call these sets disjoint. You actually use intersection all the time. It has a very common real-world connection. Think about e-commerce filtering. When you search for laptops, the website finds all laptops. Let's call this set A. Then you click the On Sale filter. This finds all items that are on sale. We'll call this set B. What you see as the result is the intersection of those two sets. The website shows you only the items that are laptops and are on sale. Like other operations, intersection has some key properties. First, it is commutative. A intersects B is the exact same thing as B intersects A. The order doesn't matter. Second, it is associative. If you have 3 sets, it doesn't matter how you group them. Grouping A and B first gives the same result as grouping B and C first. Third, we have the identity property. If you intersect set A with the universal set, that is, everything, you just get set A back. The only thing they have in common is, of course, set A itself. And finally, intersection with the empty set. If you intersect set A with the empty set, that is nothing, the result is always the empty set. They have nothing in common because the empty set has nothing to share. Let's do one final side-by-side comparison of union versus intersection. We will use the same 2 sets for both. A is 1, 2, 3, and B is 3, 4, 5. For the union, we take everything from both sets. The result is 1, 2, 3, 4, 5. Now, for the intersection, we only look for what they share. In this case, only the 3 is in the overlapping region. The result is just the set containing 3. So let's summarize what we've learned. First, intersection finds the common elements between sets. Second, it uses AND logic. An element must be in set A and in set B. Third, if the intersection is the empty set, we say the sets are disjoint. And fourth, intersection is the key concept behind filtering data. So what's next? We've talked about what's in the sets, but what about elements that are not in a set? How do we describe everything in the universe that is outside of set A? In our next lesson, we will explore the concepts of complement and difference.